Okay, so we started yesterday by talking about the free particle, and I had the title wave packets, but we didn't actually get to the wave packets yesterday, you know what I mean, Monday. So we will be looking at wave packets today. One thing I want to point out here is we have a picture here. One says X space, one says K space. Do you know what those mean?
K space, I'm not sure. X space, I would assume that would mean like physical space. I don't know how else to.
I've been using the term, instead of X, I've been calling it just position space. Does the blue show up with good contrast?
Yeah, that's fine.
Okay. So I've just been calling that position space. Now the K, I usually refer to the K space as momentum space. It's not exactly momentum. It has to do with the frequency. And of course, if it's a photon, it has its energy and its frequency are related, and its momentum and its frequency are related. So there is a relationship there for a photon. But more generally, the K there is the wave number. I'm pretty sure it's still the wave number, which has to do with the wavelength or the frequency. So that's a different variable to describe the same thing. So these two pictures, which of course I'm taking on faith, I didn't do any calculations, are showing the same exact wave. One showing how it varies in position, and one showing how it varies in different wavelengths present. Now, one thing about the Ks is you have positive and negative K. The positive K and negative K, we'll look at later, but it would have to do with the direction of the wave. So these are defining or describing the same wave function. Now you look at those and you're like, how is that the same wave function? It doesn't have the same shape. And it's because you're graphing it against a different variable. But the same information is in both equations, in both graphs. So that's something we're going to talk about a little today. We'll be talking about Fourier transforms and transforming between those spaces. So we started with this last class period. For the free particle, the Schrodinger equation, potential energy is 0, so the Schrodinger equation is very simple. And that's a second order linear differential equation, which gives us a solution of this, where K is square root of 2me over h bar squared. So that's the solution for a free particle. And this free particle this equation cannot be normalized. In quantum mechanics, is that a problem? Yes, it is, because our Schrodinger equation needs to give us a wave function that's normalizable, and this can't be normalized. So it's not really a quantum physics solution. It's a solution to the Schrodinger equation, but it's not a quantum physics solution. So that means that the things we learn from this are not exactly, this is what goes on with a free particle, but it's going to be applicable to other cases like a wave packet that is normalizable. And I'm sure I've mispronounced normalizable. It just never rolls off my tongue right. Yeah, thanks for not caring. Another thing here, because it's free, the Ks can be anything. There's no limit on the Ks, no quantization. And even if you looked at this graph, you might have noticed there's no quantization in those Ks either. Right? There's not this discrete value, this discrete value, this discrete value. They're continuous. So with the wave packet, even though we're calling it quantum physics, it's not quantized for the wave packet. So let's move on. I mentioned last class period the difference between the group velocity and the phase velocity. So if you take the time-dependent solution for a wave, now this wave is only traveling in one direction. Indy and I went over this Monday. And so Indy, is this wave here going, it says, I can't put my hand over the word either. I was going to say, is it going to the right or to the left? It says it's going to the right. How do you know it's going to the right? besides the fact that the word says to the right.
By the exponent. Yeah.
Okay, what about it?
So if you set the exponent equal to 0, I guess you can see that x is getting greater as t is getting greater, and so you can see that they're going in the same direction. So as time goes on, x is getting more positive, so going to the right. Yeah.
Okay, so here I did it different than we did on Monday, just to give you the feel. We set this exponent equal to a constant. We say, okay, we're going to look at a specific amplitude on the wave function and see how that is traveling. And so if we're keeping that amplitude constant, we just set the exponent to a constant. And then we say, well, what is x if the exponent is constant? And so I just took this and I added the h bar k squared over 2m times t to both sides, and I divide everything by k. So instead of having a k squared, that's just a k. Well, 0 would be incorrect, of course. It's a k to the 1 power because I divide out one of the k's. So this is a correct and true equation now for looking at one constant displacement. And so then you look at this, and this is as time increases. This is exactly what Indy said. I'm not correcting him. I'm just making sure we get the full explanation for Chris. As time increases, the x is increasing. When Indy and I did it, I just set constant equal to 0 because why not? It's a constant. It could be anything. 0 is a perfectly good constant. And so if the signs of these two terms are opposite, then it's going to the right. If the signs are the same, both positive or both negative, then it's going to the left. Very simple to identify. Now you'll notice, excuse me, going from the first one to the second one, this term right here has been replaced with omega. So omega is just defined as h bar k squared over 2m. So that omega, angular frequency, k, wave number. So we have e to the I parenthesis kx minus omega t. Now we can calculate the group velocity and the phase velocity two different ways. So once again, we talked about this on Monday. The phase velocity is the speed at which the actual wave is traveling. And to find that speed at which the wave is traveling, we just take the omega divided by k. That is, if I were to take this equation that I found here, the one that's in the pink or magenta, and I take dx dt, dx dt by definition is v, right? And so dx dt is equal to the phase velocity. And so if I just take this derivative, it's very simple. It's going to be h bar k over 2m. And so another way of looking at that derivative, because it was linear, is that the phase velocity is just omega over k, right? Omega is what time was multiplied by, k is what x was multiplied by. So x over t is omega over k. So the phase velocity, that's how fast the wave is traveling. The group velocity is how fast the packet is traveling. The packet is made up of multiple frequencies that when added together give you a superposition that gives you a pack. And so to determine how fast that packet is going, we take our equation and we take d omega dk. So in that case, since omega was, I've got to change color. It's getting too much of one color. This is omega. So if I take the derivative of omega with respect to k, right, k squared, bring down the 2, k, and then we have the 2's cancel. And so it's h bar k over m. And you notice these are not the same. The phase velocity is 1/2 of the group velocity. The packet's going twice as fast as your wave is traveling. Kind of doesn't make sense, but as Indy and I talked about on Monday, the group is not the waves, it's not the stuff that's limited. So that the group can be at a different speed. But there is some kind of question about how are they different. And if you read the textbook on this, which you may or may not have, I'm not going to push you. He says, there's a problem. We'll get back to that later. And then how does he resolve the problem? Do you remember how he resolves the problem?
Fourier transformation.
Well, he gets down to the end of the transformation and says, oh, look, we can't transform it back. It's impossible. Hence, it's not really a problem because, yeah. But then he also waves his hands to and this is what it would have meant. So now we're going to do some Fourier transforms. So we are going to transform from our solution at time equals 0 to our K space, or as I call it, phase space or momentum space solution. And we do that with an integral from minus infinity to infinity of whatever our wave function is, multiplied by e to the minus ikx dx. Integrate it, and you have done your transformation. And then if you want to transform it back to psi, and notice this is adding time. That had at time equals 0. Now we're adding at any time. And you have this in the reverse transformation. Notice the sign for the original transformation from position space to phase space, there's a minus sign there. For the transformation back, there is no minus sign there. But we do have this additional term, which I know has a minus sign, but that's not the important one, with the time to convert it back and get a time-dependent solution. So you know what we're going to do, this. So we have to do it with an example problem. So I took the example problem that's in the textbook. Why did I choose the one in the textbook? Well, number one, because afterward, if you don't understand, you can go and read the textbook explanation. And number two, because these are kind of hard, and I wanted to make sure that I didn't go off and choose one that would be too hard for me. So here's our textbook example, example 2.6. We have a free particle that's constrained to be in a region from minus a to a. So that means we have our wave function that's supposed to be a nice square box, okay? It looks not like that. So we have a minus a. So the box has a width of 2a, obviously. Is this normalizable? The wave function is 0.
It's a free particle.
It's not free. It's not free. It's constrained to be in this box. Now, it's not a particle in a box. It's not an energy box. It's saying that we just have it somehow constrained in this box. And so its wave function is 0 anywhere for x is greater than a or less than minus a. Hence, it's not diverging for large x's, and it's just constant in between. That's normalizable without even doing math. Well, without doing calculus. I mean, what is it if it's not calculus? It's hardly math, right? Right, Chris?
Yeah.
Obviously, there's a lot of math that's not calculus, but for physics, we didn't learn group theory in my school, so it was just either linear algebra or calculus. So we can normalize this. The integral, since it has an amplitude of a inside the box, the integral of a constant, of course, is just a mod squared, well, because you're doing the integral of psi mod squared. It's a mod squared times the width of the box 2a. And so you very quickly say for that to be equal to 1, you have to have a is 1 over the square root of 2a. So very easily normalized. So we've gone past the problem for the free particle not being normalizable because it's free, but it's constrained to be in this region initially. How is it constrained? Not my problem. But at time equals 0, it's within this region. After time equals 0, it could be wherever in the world it wants to be. That's where the free comes in. Because Indy was taking, it's a free particle, hence not normalizable. But with our constraint of it starts in this region, then it was normalizable.
Okay.
So now we're going to take the Fourier transform. And you've got to admit, this is pretty much the easiest possible problem we could do, right? Because it's a constant for the psi. So to do this Fourier transform, here's the equation for the transform. So we substitute in that psi. So here is the normalization constant, A, and then it's times 1, so it's just A, e to the minus ikx. So this here is the psi of x, and notice the limits are only going from minus A to plus A because it's constrained to be in there. Well, if you do this integral, what's the integral of e to the minus ikx?
I want to say it's pi over a to the 1/2. But I feel like there's a constant or a value.
It's
Well, evaluated.
because it's an exponential. Exponentials, remember, an exponential, if you're doing the derivative, you're going to bring down the derivative of the exponent. If you're doing the integral, you're going to divide by the derivative of the exponent. So that's going to be e to the minus ikx over minus ik, and then with our limits.
Yeah, for some reason I'm thinking a Gaussian integral, not.
Yeah, not just the simple. Yeah.
Yeah.
Yes, because it would be much more complicated if it was Gaussian. Yeah, and if you have your Gaussian tables memorized, well, kudos, because I sure don't. So we have putting in I brought out the 1 over minus ik. I'll worry about the signs and whatnot at the end. And then I'm going to have putting in my limits e to the minus ika minus e to the minus and minus makes it plus ika. No mistakes, I don't think. No mistakes, I don't think. That was really good grammar.
Okay, we're not in the meters. Doesn't matter.
You're a very forgiving group. Well, I'm going to now take this, and I'm going to bring in the minus 1, and I'm going to multiply top and bottom by 2. So this is equal to 2 over k. Since I brought in the minus 1, I'm going to change the order. E to the ika minus e to the minus ika all over 2I. And now, oh, Chris, the math major, what is in parentheses?
What?
What is the value of this thing here in parentheses?
I want to say something, but I don't feel like that's right.
That is a definition of sine of whatever the I was multiplied there in the exponent. Sine is, let me just write these down.
Yeah. Oh, yeah, because the, yeah.
Those are another way of writing the Euler relation.
Yeah.
That e to the I theta. It all comes from the same basic thing. So what we have now is this integral part is equal to 2 sine of Ka over K. So now we can come back over to what I had written on the paper, and the square root of 2a and the square root of 2 pi, both 1 over. Those were not part of what I was looking at. I was just looking at the integral, not with the constants. So I had a 1/2, and then on the bottom, square root of pi a, and then this stuff. So when I brought it all together, the 2 that I took was just this 2 here. So I'm going to get rid of the 2 that I added in. And I have, in the end, once again, just too much of this color. In the end, my phi I'm getting new tips. They're ordered. Then the pen will stop skipping. It wasn't in your class, but this new Surface Pro 4 pen is super slick, which is why I now have tape on it. And in class, I dropped it like from this height straight down on the tip, and it caused this black sheath to slide up over the end of the tip. And so it was kind of blocking. And so I took that little black sheath off at the very end, just broke it off. And now it's not supported, and it will then skip and judder. Just so you know why my handwriting is even worse than normal this last week. Okay, so we've successfully done a Fourier transformation of the easiest thing possible. I mean, it's the easiest thing possible. We're still good, right? We did it.
Yay.
I don't remember if it's from what it's from, but I'm singing the stupid little song. Yay, we did it. Oh, it's like Dora the Explorer, isn't it?
I don't even know.
My niece and nephew used to watch Dora the Explorer all the time, so yeah, pretty sure that's
Yeah,
what.
That sounds like something from Dora the Explorer.
Okay. Now, I did not follow the textbook on from here because the textbook says, okay, now let's do the next transformation, that is the reverse, to get it back to psi as a function of x and t. What would we have done? Well, we would have just had a time component. And so it shows the integral, and then it says, oh, but look, cannot be done. What do we do now? Cannot be done. And so I took out the cannot be done part. I didn't want to just write something down and say cannot be done. You can look in your textbook and see cannot be done. But the textbook does take this and draw some conclusions that are useful to us. It says, okay, we can't take the inverse transform, get back to psi as a function of x and t from this. But we can take some limiting conditions. What if a is super, super small? So that within the range, of, well, if a is super, super small, then we could use the small angle approximation that sine Ka is approximately equal to Ka. Well, no, it is approximately 0. That's true. But we throw away the first order term because that didn't help us, right? We always keep the first term that's non-zero.
Yeah.
So if a is super, super small, I just replace the sine Ka with Ka, and then we say, oh, look, the K's cancel. Woohoo, got rid of my variable, now it's inverse transformable. And so you can do the inverse transform of that. By the way, notice that's equal to square root of a over pi now. Oh, so then we can do the inverse transform. And what do we find? We find that if we have our particle starts in a very well-known position. Okay, so going back to what we've been doing, we said our particle is constrained to be in a region. If we make that region constrained to be very small, then we know exactly where it is. I mean, exactly is not the right word, but pretty precisely where it is. And what do we have for the phase space solution? Well, the phase space solution is going to be just a constant. We have an even amount of all of the different possible wave numbers, which means that since momentum was proportional to k, that we have no idea what the momentum is. It's equally probable at all momenta. So we know exactly the position, but what do we know about the momentum? Nothing. We have no idea what the momentum is. Kind of the key there with the uncertainty relation. If we know one of them really precisely, then we have no idea of the other. Going back to that joke with Schrodinger and Heisenberg, and I can't remember the other one. You know, do you know where you are, or do you know how fast you were going, sir? No. You were going 35. Well, great. Now I have no idea where I am. Right? That's what is illustrated by this. And of course, that's an unreasonable joke, but a very funny joke if you're a big enough of a nerd, okay? I clearly am, or I wouldn't refer to it as a very funny joke. Now, if you did the reverse of this, if you made the box super, super broad, then you would have no idea what the position is, but you would have just one k value. And so, it works in both directions. So now we're going to go to the Gaussian wave packet. This has a fair amount of math, which thankfully I just wrote the answers to as we go on. I was looking at the time like, oh, am I going to have to work all through this? So a Gaussian wave packet, now Chris can use his comprehensive knowledge of Gaussian integrals. I say that tongue in cheek. We just know that I don't have a comprehensive knowledge of Gaussian integrals, and I took the paper out of my notebook, or my textbook. So we're going to start now with a Gaussian distribution. At time equals 0, we have a Gaussian distribution of particles. The first step is to normalize. Is this different from our homework? I mean, we're not going to change our homework into phase space, but I think that's what we had for the homework, isn't it?
It's very, 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 very close. It's actually, it's number 3B is the normalizing.
It's, oh. Okay, yeah. This is AX, so it's very different. That X makes a world of difference.
Oh, that's right.
I didn't notice it when we were looking at earlier today either. So it's not the ground state for the simple harmonic oscillator. Otherwise, it would have been the same thing. Okay, so first step is to normalize it. So we normalize this. Psi mod squared is going to be a mod squared e to the minus 2ax because there's no imaginary in the exponential part. And so if you use your comprehensive knowledge of the Gaussian integrals, then you get 1 is equal to a mod squared times that square root of pi over 2a. So the square root of pi over 2a is that Gaussian integral. Go ahead.
Quick question.
Yeah.
Should there be a factor of 2 since we're going from negative infinity to infinity and our Gaussian integral we multiply by 2 because it's an even function?
Let's look at the table and see if this is, I mean, I can't say yes or no because I have just that kind of comprehensive knowledge. Gaussian integrals. So the integral of...
Oh, no, because it's the 1/2.
Yeah, it's got the 1/2. Yeah. Okay. I mean, I wish I could say, yes, I know my Gaussian integrals, or yes, I know I did it perfectly, but I can't come up with either of those two.
Yeah.
Okay, but it is right because, yeah, I had the 1/2. So if that's equal to 1, this equal to 1 is just repeating what was on the other side of the equation. Then I can divide both sides by square root of pi over 2a, take the square root, and I get my normalization constant. Just a practice step, really, to make sure we can normalize it. Did somebody have a question? No? Okay. So now that we've done that, now comes the hard part. Now we're going to apply that Fourier transform. So here's our equation for the Fourier transform with the minus sign here. And so putting in my function, does this look like a fun function to integrate to you?
Of course. Fabulous.
Yeah, it looks easy enough. Now we can combine those into one exponent.
I'm pretty sure the Calc 1 students can do that.
Yeah.
I was thinking about an integrated Calc 1 here.
My son's in Calc 1. I'll give it to him and see what he does. Of course, they just had their first test, and of course, they've only learned derivatives. But you know.
Yeah. Just think of it as the opposite of a derivative and see what you can.
Yeah, I mean, how hard can it be? You learn a derivative, just do the opposite. Okay. Now, because Christopher is a math major, I'm just going to ask, do you have a trick for solving this? Because there is a trick for solving it. Do you know it offhand or no?
No, I can't say that I do, other than using substitution.
Well, it is a substitution.
Yeah, I just don't know the substitution.
Complete the square.
Oh, yeah.
So basically what I'm going to say is I have minus ax squared minus ikx plus something equals y squared. And so now I just have to figure out, well, what could that be? And so minus sign, going to have that, right?
Yeah, right.
And then for my cross term is going to have 2 times, that is,
Doesn't have to be a square root or a factor.
I'll put 2b. Actually, 2 square root c. It has to be the middle term has to be 2 times the first term times the second term. And the second term is going to have to be square root c, right? We'll have to have that squared. I mean, that's what it's going to have to be. Just doing complete the squares, that one. And so we just want to find what c is. So the middle term, that is equal to minus ik. Did you follow me or did I lose you completely?
You can keep going.
You can keep going. We'll figure it out later. Okay, I'm going to back up. If we're going to complete the square, for the first term, I have to have the square root of minus a.
Right. Which is I.
And for the second term, I have to have the square root of my c. And so then if I were to actually expand that, I would have squaring this I'd have that. And so what I had written was this here, 2I square root A square root C, and then I'll put my x, has to equal this here minus IKX. I didn't write the x's because I had an x in both terms. And so that allows me to solve for what C has to be. And so if I solve this for C, first solve for square root of C, notice my i's I can cancel. So square root of C must be minus K over 2 square root A. So C is equal to K squared over 4A. So that's probably the longest complete the squares you've ever done, mostly because I didn't actually practice doing it beforehand. So if I take this, my exponent here, this right here, is equal to y squared minus c squared, or y squared minus, oh, not c squared, y squared minus c, which is equal to y squared minus k squared over 4a. But that gives me an easier looking integral. Yeah, yeah.
Doesn't that become dy?
Right now, this is correct. But I'm going to have to shift it to dy if I'm going to do my integral right. So looking back at my definition, I erased it, but I had written down that y must be equal to I square root of a, or x. That's what y has to be. And so what's dy equal to?
I squared it. Yeah.
Now, I'm afraid now I may have made a mistake because that doesn't seem right. Let's go back to what it actually gives us. So y equals, oh, yeah, there you have it. Yeah, y. Whoops. I was close. I was close, but not correct. Yeah, in my C term, I have a little bit of an error. So y is square root of ax plus ik over 2a. I kind of screwed up. Sorry. Hence my longest form. I mean, this here is a correct number, but here is where things went sideways. Well, actually, maybe it's not even correct because 2 squared a. Yeah, I messed up there. Looking for the clock to get some relief when I mess up.
Okay.
So here's the y for what I was planning on doing when I did the lecture was just showing that, look, if I take that y and I square it and I add k squared over 4a, then I get ax squared plus ikx. That's what I was looking to do when I first did it. I went off the screen. So we have this substitution, which was almost what I put. So y squared, and then it's plus instead of minus. So that all looks the same, except for then dx is equal to square root of a times, or dy square root of a dx. So dx is 1 over square root a dy. So there I used dy is square root of a dx, so dx is dy over square root of a. That's where this over square root of a came from. So that's what this integral up here becomes. Now, that's a Gaussian integral. That being a Gaussian integral, wait, there's one more thing I did wrong. Minus there. It was e to the minus wow, yeah, sorry about that. See the minus sign that's factored out right there? Let me change the color, make it so it really stands out. The minus sign that's factored out right here. That's a piece of this here. So now it's a Gaussian integral. This here, if we look at our Gaussian integral table, once again, that's the same thing that we just did. Going from minus infinity to infinity, it's going to have the 2 on there, so it's going to be 1 over, or square root of pi over, yeah. And the 2a there is just 1. Assuming that I remember the integral table right, and of course, how will we check? By coming over here. And yeah, I distributed things differently, but I think that's the same. So doing that whole stinking integral and then collapsing all of our square roots here, there, and everywhere, you get to the final equation that phi is equal to this Gaussian distribution in K. So we have a Gaussian distribution in position space gave us a Gaussian distribution in the phase space, or in K space. So now we have 2 Gaussian distributions, and we can find what the uncertainty is in position and the uncertainty in momentum, and check again to see if Heisenberg's uncertainty relation is confirmed. So how would I don't have any slides for that, but how would I do this? You're doing it in your homework. How do I confirm or verify the Heisenberg uncertainty relation now that I have the phi of k and the psi of x?
You have to find the standard deviations, right?
I have to find the standard deviations. To find the standard deviation, I can just find the standard deviation for k's in k space and for x's in x space, and it tends to be easier work. And so that's, this is laid out so you have a graph like this and the exact same calculation for what the standard deviation is will be done for both the phase space one and the position space one. And so you get your uncertainty in K, and then we have to convert from K to momentum. And if I remember right, wow. Isn't that right? Momentum is h bar k. Oh, no. Yes. H bar k because it's over 2 pi. The 2 pi's cancel.
There's an I somewhere in there, I think, too.
No. The k's are real and the momenta are real.
Oh.
This is just converting from the k variable to what that means for momentum using the de Broglie relation. And k is equal to, I think, I thought it was 2 pi over lambda, but if it's 2 pi over lambda, then oh yeah, no, that's right. So if K is 2 pi over lambda, then lambda is equal to 2 pi over K. And so this is equal to, and that gives you the H bar K. Okay, so I didn't do the uncertainty calculations here. Instead, I went straight to, now let's get a time-dependent solution. Now, backing up, this was not a time-dependent solution. This was the initial state. Over time, it's not going to stay in that state. And so to get the time-dependent solution, now we go back to this equation that I had on my Fourier transforms page, which is equation 2,100, and we do the calculation. And when we do that calculation, if you put in the phi that we just found, 1 over 2a pi to the 1/4 power, so I should have, where am I 1 over 2a? Why is the 2a on top? I don't know why I have a different value here. Well, actually, what I do know is that I did this one late last night, so this one here is the one that has it wrong. I got the 2a in the wrong place because I was trying to copy and paste from this equation to that equation, and clearly I didn't copy and paste right. So that there has to be just a 1, and the 2a is on bottom. This integral now has k squared over 4a I kx minus h bar k squared over 2mt. You look at that, and you know what you should say to yourself? You say, shoot, I don't want to do that integral. And that's exactly what I said. So I went to the answer. It can be shown by somebody who's more mathematically astute than I that when you do that integral, you get this crazy function. And of course, the 2 pi is brought into that as well. And this constant here is correct. That's probably where I copied and pasted from. So it can be shown that this is the answer you get. If time is 0, we should be back to where we started. If time is 0, then we have minus 2ax squared over 1 divided by square root of 1. Is that where we started? We had this stuff, e to the minus ax squared. Uh-oh, I said 2 and that had no 2. Oh, yeah. Okay, so I still have a mistake. This is a mistake in my slide because when time is equal to 0, that's 2 instead of 1. I'm going to have to go and revise this slide and start next class period just by having the correct answer. But what we have is now a function that's going to show a spread. So it started confined to this Gaussian packet, but the Gaussian packet is going to spread out over time. And so it's not going to maintain its shape. And that's where we'll end. So next class, next class period, I will check this equation, get it right, and we'll move on.
Okay.
Before you guys go, next Friday, did you check Indy to see if you're going to have an event next Friday or not?
I don't have anything this Friday.
Bummer. Now, this Friday, I'm going to be here. We're having class this Friday. I would like to try to make up the class at some point because, you know, we will drop behind if we miss the class.
Yeah.
Options would be for me to meet tomorrow, or I could meet with you sometime like Monday or Wednesday afternoons, or after I get back from the funeral. I don't know what your schedules are at all, so I'm,
Mondays would be the best day. Just Wednesday that anytime, yeah. I'm free after this class.
I just have,
Is 3:15 on Monday afternoon? Or I guess.
okay, right now, what time is it for you? It's 2, right?
2 o'clock.
Okay, so 3:15 would be 2, yeah, I can do that. Okay, so we'll just have 2 lectures on Monday.